You know, I love breakfast cereal. There's nothing just like cold, rich milk with some crunchy, weedy, nutty, ricey, whatever it is. It's just so delicious. I can eat cereal any time of day. So good. Our company, called Epsilon Industries, has hired a consultant to analyze the profitability of the breakfast cereals that we manufacture. Now, the consultant's models have determined that the profit from selling the cereals in millions of dollars depends on the amount of engine oil in grams that we put into each box of cereal. And that profit depends according to the following function. So this function has input x, the grams of engine oil that we put in each box, and its output p of x is given by the square root of 5 cosecant x minus the square root of 10x plus 40. And that's in millions of dollars. Okay, there's one more wrinkle to the puzzle, which is that due to health regulations, we are only allowed to use between 7 pi over 6 and 11 pi over 6 grams in each box. So this means that the x variable is constrained to live in the interval between 7 pi over 6 and 11 pi over 6. Now the question is, what amount of engine oil will give us the largest profit? Okay, so in other words, what do we want to do? We want to maximize the profit function p of x on the interval from 7 pi over 6 to 11 pi over 6. Alright, so from here on out, it's just mathematics. We're going to follow the same three-step program that we've used before to find the maximum and minimum values of a function. The first step is to find the critical values. Those are the x values where the derivative is 0. So remember, I'll rewrite the function that we want to optimize. It's the square root of 5 times cosecant of x minus the square root of 10 times x plus 40. Now it's really important here that that x is not inside the square root of 10. Okay, it really is just the square root of 10 times x. I could even put it in parentheses to emphasize that fact. To find the critical values, we need to compute the derivative, set it equal to 0, and then solve for x. Here we go. So for this first part of the function, we need to remember the derivative of cosecant. Well, just as the derivative of secant is secant times tangent, the derivative of cosecant is the same thing, but with a minus sign and the corresponding co-functions. In other words, the derivative of cosecant is minus cosecant times cotangent. Since the constant root 5 was out front, we got to keep it around. Next up, the derivative of minus root 10x is just this constant minus root 10. And the derivative of 40, that's just a constant, that's 0. So we set the derivative equal to 0, and we solve for x in order to find those critical values. All right. Let's see, we can move the root 10 to the right-hand side of the equation, and then we can divide by minus root 5. I'm going to do that all in one step. You might want to fill in the details. If we move the root 10 to the other side and then we divide by minus root 5, we'll get minus root 10 over root 5. The root 10 becomes positive on the right-hand side, but we're dividing by minus root 5. So the overall number is negative. Okay, there's some cancellation here because the square root of 10, 10 being 5 times 2, is the square root of 5 times the square root of 2. If we rewrite that number that way, the square root of 5's cancel, and so the right-hand side is just minus root 2. Continuing onward, we're going to rewrite the left-hand side in a different way. We're going to expand cosecant and cotangent in terms of the cosine functions that define them. Cosecant is 1 over cosine. That's not right. It's 1 over sine, right? don't make that mistake. Just because there's a co, that doesn't mean it's 1 over cosine. It's 1 over sine. Careful with that one. What about cotangent? That's the reciprocal of tangent. It's cosine over sine. So that is the cosecant and cotangent functions written in terms of the basic trig functions. So overall, what is this equation saying? If we combine the sine terms in the denominator, it's saying that cosine of x divided by sine squared x is equal to minus root 2. Remember, we're trying to solve for x. Okay, how are we going to solve for x in this equation? Here's an idea. Let's use the following trig identity. That's the old cosine squared plus sine squared equals 1 identity. That comes from the Pythagorean theorem. Super useful. If you isolate just sine squared of x by subtracting cosine squared from both sides, you can rewrite it as sine squared equals 1 minus cosine squared. Now I'm going to take that sine squared there in that identity, and I'm going to sub in for the sine squared that we have in the equation that we want to solve. When we do that, we get cosine of x divided by 1 minus cosine squared of x. That comes from replacing the sine squared, and the right-hand side stays the same. Okay, looks good. Continuing onward, how do we solve this equation? We have yet more work to do. We now need to multiply both sides by 1 minus cosine squared of x. Why am I doing that? It's because I want to clear the denominator on the left-hand side. I'm anticipating that we can write everything in terms of cosine. Okay, so check it out. Oh, I've made a fundamental error. Do you see it? Do you see my fundamental error? I'm getting too excited about what our profit's going to be in millions of dollars. There is a minus sign here in front of the root 2. I forgot to carry that along. That's got to be there as well. We got a minus root 2 up front. Okay, with that correction in place, let's expand this right-hand side. We'll have a minus root 2, and then minus root 2 is multiplied by minus cosine squared. Two wrongs make a right, especially in the breakfast cereal industry, and so we get plus root 2 cosine squared of x. Now I'm going to move all of the terms to the same side of the equation. I'm moving them to the right-hand side, but I'm going to write that new term on the left to make it look like a nice quadratic equation. Check it out. So the root 2 cosine squared and the minus root 2, they were already there, but I subtracted cosine of x from both sides of the equation. Okay, now here's the final trick. We can actually solve for cosine of x in this equation in the following way. I can treat cosine as just some new variable y. I'm just going to treat it as a new variable for a second and solve for that variable, and then solve for x. If we do that, we have the equation root 2 y squared minus y minus root 2 equals 0. And when we write it that way, it's less intimidating. That looks like something we can actually solve. We can find the solutions to that equation using the quadratic formula. So our b is minus 1, so minus b is minus minus 1, plus or minus the square root of b squared minus 4ac. And one of those root 2's was minus root 2. I'm dropping my minus signs here. Got to be careful there. So again, that's b squared minus 4ac. Notice that the c, that coefficient, has a minus root 2. And now we divide by 2a. That's 2 root 2. Okay, very good. What do we get? Two wrongs make a right. Minus 1 squared is 1. And what's going on here? Again, two wrongs make a right. Those two minus signs multiply to give plus. And then we have root 2 times root 2. That's 2. 2 times 4 is 8. So that's what we get. And now we're starting to get somewhere. 1 plus 8, that's 9. So we're taking the square root of 9. That's 3. All right, almost there. The two options are either plus or minus. If it's plus, we get 4 over 2 root 2. And if it's minus, we get minus 2 over 2 root 2. Okay, now we're almost done. I just want to simplify these two possibilities for y. Well, there's a common factor of 2 here, so it's going to be 2 divided by the square root of 2 for that first term. And then what happens here, there's a lot of different ways you could do the cancellation here. I sort of like this one. This is pretty efficient. If I rewrite the 2 on top as the square root of 2 times the square root of 2, right? The square root of 2 times the square root of 2, that's just 2, right? Because the square root of 2 squared is 2. If I rewrite it that way, then I can cancel one of those root 2's with that term in the denominator. And so we get minus root 2 over 2. That's good. That looks a little more familiar from the point of view of outputs of trig functions. Remember that y was just our new name for cosine of x. We're ultimately trying to solve for x here. Y was just the name that we gave to cosine of x to solve the quadratic equation. And now check it out. Cosine, as a function, it's always bound to lie in between -1 and 1. Right? The cosine function is oscillating between -1 and 1. And look at this number that we found for y, the solution for cosine of x, 2 root 2. Since 2 is larger than the square root of 2, that number is bigger than 1. And so that number is impossible. It's a valid solution to the quadratic equation, but it is not possible for that number to be the output of the cosine function. So that is not going to happen. We can strike that from consideration. And the only possibility is that cosine of x is equal to minus root 2 over 2. Okay, now we're almost done. Remember, we're trying to solve for this critical value here. It's gotten a little bit difficult. All right. Where in the world is cosine equal to minus root 2 over 2? That's the angles like pi over 4 where cosine and sine are equal. But because of that minus sign, we have to be in either the second or the third quadrants. Those are the points where cosine is minus root 2 over 2. What are the angles here? Remember that this is 0 and halfway around is pi. So this right here, it's a pi over 2 and then another pi over 4. So that one's 3 pi over 4. What about the other angle down at the bottom going all the way into the third quadrant? Well, that one is going to be pi plus pi over 4. That's 5 pi over 4. Sorry, that 4 got a little hidden by my hypotenuse, the radius of the unit circle. It's 5 pi over 4 there. Okay, so those are the 2 points where the cosine is minus root 2 over 2. But there's one more fact we know. Remember, the government has determined that we're only allowed to use between 7 pi over 6 and 11 pi over 6 grams of engine oil in our breakfast cereals. That's the amount of grams per box. So the x variable is constrained to lie in between these 2 angles. All right. Now, where are those 2 angles on the unit circle? Well, let's see, 7 pi over 6, that's a little bit past pi. So that's like this one. That would be 7 pi over 6 starting from 0. And 11 pi over 6 is almost a full revolution around the unit circle. It only misses 2 pi by a factor of pi over 6. And so this is the range of acceptable engine oil on the unit circle. We have to choose an angle in between these 2 angles. That means that 3 pi over 4 is not a possibility, and in fact, the only possibility is that the value of x that we seek is 5 pi over 4. That's that angle that got hidden there by the purple ink. That was the other angle where cosine is minus root 2 over 2, and the angle x is in between 7 pi over 6 and 11 pi over 6. So that is our only critical value.
But I think that's exactly the problem. It's not just the Berlin speech, but in Cairo he said, any world order, he said, any world order.
I'm laying down a beat for you. Keep going.
Any world order that elevates one nation over another will fall flat.
Oh, snap.
I think that goes against the idea of American exceptionalism.
Exceptional fast food and exceptional dance moves.
Most Americans believe that this country was gifted by God, a blessed nation, and that we are better.
Yeah, we the promised land, a sacred place. Getting blessed by Joe Biden from space.
God bless America! God bless America! God bless America!
We're not quite done yet. That was only the first step to find the critical values. Remember, there's 3 steps. In the second step, we need to plug into the original function, in this case the profit function. Now it's an important point that we do not plug into the derivative. We don't want to optimize the derivative. We want to find the maximum profit. So we got to plug into the profit function. Okay, first we plug in at the critical values. We just found that 5 pi over 4 is the only critical value that's relevant. The only critical value that's in this window of acceptable amounts of engine oil that we can put in our cereal. Alright, so I'm plugging in 5 pi over 4 into the formula for our function here. It looks pretty complicated. That's okay, let's just analyze it one piece at a time. The most important thing here is the cosecant of 5 pi over 4. How do we figure that out? Remember, cosecant is 1 over sine, okay? 1 over sine. What's the sine of 5 pi over 4? Well, 5 pi over 4, it's down there in the 3rd quadrant. It's that equidistant point where the cosine and sine are the same. So the sine of 5 pi over 4 is minus root 2 over 2, and therefore the cosecant of 5 pi over 4 is 1 over minus root 2 over 2. And now at this point we could leave that alone if we just wanted the output in terms of a formula like that. But we're going to need to compare values, so let's plug that into a calculator. If you plug that into a calculator, you get a little over $24.4 million. That'll be our profit if we use 5 pi over 4 grams of engine oil. Alright, we also need to plug in the endpoints of the interval into the profit function. And that's because it might be that because of the way this function is being cut off at these endpoints, it might be that the largest profit that we can make is actually happening at the endpoints and not at one of those points where the derivative is 0. So let's copy down this formula. There we go. What's cosecant of 7 pi over 6? It's 1 over sine of 7 pi over 6. 7 pi over 6, it's down there in the 3rd quadrant. The sign is negative, but it's closer to the x-axis. And that's one of those spots where the sign is 1/2. Well, in this case, minus 1/2 because it's in the 3rd quadrant below the x-axis. So that would be a formula. We could flip this fraction and tidy it up, but I don't really care. I just plugged it right into a calculator and figured out the actual number. In decimal form, it's 23.9 and thereabouts $1,000,000. So that's the value, that's the profit that we get if we use 7 pi over 6 grams of engine oil. Alright, and now finally we need to plug into the end of the endpoint, the right-hand side of the endpoint, the final value for x there at the right of the acceptable values. That's the most amount of engine oil that we're allowed to put in our breakfast cereal, according to the FDA. What's the cosecant of 11 pi over 6? That's 1 over the sine of 11 pi over 6. But if you look at the unit circle, 11 pi over 6 and 7 pi over 6, they're across from each other. They're at the same height. So actually that is the same as what we got plugging in 7 pi over 6 into the cosecant function. But here in the next term, the 11 pi over 6, is different than the 7 pi over 6, so we are going to get a different number. In this case, we get $17.3 or so million. Okay, so we've plugged in the critical values. We've plugged in at the endpoints. The final step is to compare the outputs. See which is biggest, which is smallest. All right, let's look back at our various profits that we've calculated. So at the critical value of 5 pi over 4, we got $24.4 million. And then at the endpoints, we got 23.9 and 17.3. The largest of those numbers, the maximum profit that we can hope to obtain, is this one. It's the $24.4 million. That's the most profit we can make, according to this model. And so we can go and report to the CEO of Epsilon Industries that if we use 5 pi over 4 as our amount of engine oil, if you compute it out, that's about 3.93 grams of engine oil in our product. Then that's the X values that will maximize the profit. So using that amount of engine oil, we maximize profitability. Fantastic. And we can expect to make about $24.4 million in profit using that X value. All right. Okay, we can actually say a little bit more. Our CEO really likes graphs, so in our presentation of our analysis to the CEO, we're going to include a rough sketch of the graph of the profit function. The profit function starts a little bit past 3 at 7 pi over 6, and the value there at the left endpoint of the interval, what was it? It was about $23.9 million. So the graph starts around here at about 23.9. It raises up quite quickly to its maximum value of 24.4, and that occurs right before 4. That's at 5 pi over 4. And then it decreases down to 17.3, and that's at 11 pi over 6. That's roughly at 5.76, so the graph looks roughly something like this. That's the graph of the profit function in the window of acceptable X values. Remember that the FDA has determined that the only acceptable amounts of engine oil that we're allowed to put in the breakfast cereals have to be in this window. Those are the allowable X values. Okay, so we see our maximum value right here. That sweet spot is hit quite soon. So it turns out that you don't want to use too much engine oil in your breakfast cereals. It's not because of taste, it's just because of the cost of engine oil. Alright? So that's because even if people like to eat more engine oil in their breakfast cereals, using more of that engine oil starts to cut into our profits. So we want to use just a little bit more than the minimum allowable threshold, right? That sweet spot that we found for the maximum profit of $24.4 million, it's occurring at 5 pi over 4, which is about 3.93 or so grams of engine oil. So that sweet spot is just a little bit over the minimum allowed value of X. Now, if we wanted to report to our CEO on the minimum possible profit, you might ask, why in the world would we care about that? Well, I don't know, maybe there's something weird with like stocks or something, like the CEO is going to like flip the stocks somehow and they'd like to make the company fail for some reason. We can at least report, just to be thorough, that the minimum profit that we'll obtain in our breakfast cereal manufacturing sector is about $17.3 million, and that's occurring at the extreme end of the allowable range of X values. That's at 11 pi over 6, or about 5.76 0.76 grams. So that's the complete report. To maximize profit, we want to use the x value that we found by solving for x when we set the derivative equal to 0. This maximum profit is occurring at that critical value.